Hello, everybody. It's Mrs. Pound, and we are working on chapter 6.3 of Light. So today's topic is going to be from section 6 through 6, the wave and particle properties of light. Our objectives for today are going to establish the three ways that light acts as a wave and describe the dual nature of light. Now, there are lots of things that have a dual nature before we get into the wave nature of light. For example, paper, we can write on it or we can burn it. Also, salt. We can use it for flavoring or we can melt ice with it. So, many things have a dual nature. And so, the first part of the dual nature of light that we're going to talk about is the wave nature of light. We know white light is a wave because light reflects. So it has regular reflection, reflection of light off of a flat surface. This is all of the waves have the same angle of incidence and angle of reflection. For example, mirrors and glare. Um, Here in the background, we have windows that are acting as mirrors and just a very crisp image. And glare is when all the light is reflecting into your eyes, say off of water, and that is regular reflection. There's also diffuse reflection. This is reflection of light off a rough surface. The light waves have different angles of incidence and reflection, and so they scatter. And so here the image becomes distorted because we have waves on the water. So the way the light waves are hitting that is they are hitting it in different spots, and the angle of incidence always equals the angle of reflection, but it's slightly different in different spots. Diffuse reflection produces images that are not clearly defined because light waves strike a rough surface and are scattered in many different directions, producing a fuzzy reflection that is not clearly defined. Light also refracts, which means it bends. Remember, it means that it bends when it's going from one medium to another. So we express this as the index of refraction. This is a property of matter that compares the speed of light in a vacuum with the speed of light in a material. And light waves travel much slower and bend farther in liquid water compared to ice. This indicates the index of refraction for water is higher compared to ice. Light also diffracts. Remember, this is bending around objects. A scientist named Thomas Young coated a sheet of glass with carbon and cut two scratches in the carbon to make fine slits. He held a light source behind the glass and observed alternating dark and light bands. So that's what's represented here, light bands, dark bands. And I know only one slit is here. There's probably another slit further over. But this is what we did with water waves as well with the wave table, if you recall. The dark bands showed a cancellation of light waves due to destructive interference. Bright bands appeared in regions that would have been totally dark if light did not diffract around the slits. So dark bands, destructive, light bands, constructive. Also, because of diffraction, we see some phenomena with shadows. A shadow is a region of darkness formed when an opaque object comes between a space and a light source. And shadows tend to have a penumbra and an umbra. Now, the penumbra is the edge of the shadow that is partially illuminated. Partially illuminated. So over here, see how it's lighter than this part? This is due to diffraction. Some light is getting around there, so we have diffraction. The umbra is the part of the shadow that is completely dark, so we don't have the light bending around the object as much there, and so there's a very dark part. We also see that with eclipses. That's where we get partial and solar or partial and total eclipses for the sun and the moon. Now let's talk about the particle nature of light. Heinrich Hertz discovered that light behaves like a particle. He found that certain surfaces emit electrons when light falls on them. So here's the light coming in, here's the electrons coming off. An increase in frequency causes an increase in electron emission. So notice these are blue, not red. There's a reason for this because red light will not produce this effect. It has to be higher frequencies, so more towards your blue or your purple or even ultraviolet will produce this effect. Now notice too, frequency and hertz. Remember, the unit for frequency is hertz. So off to the side here, right, frequency equals Hz for hertz for the unit, a capital H, lowercase z, to remind you of the connection between hertz and frequency here. A change in frequency would not cause this event if light only behaved like a wave. So what they called these, the particle nature. So forget that this is a wave and see these particles here. It's a photon, a tiny bundle of light energy that's knocking the electrons out. The photoelectric effect is what this is called. It's the release of electrons from metals by photons of light. So it has a name. It's called the photoelectric effect. And this is also called the particle theory. This is the theory that light is made of small bundles of energy called photons. And this is kind of a mysterious thing, but so is the Trinity. We don't have to understand everything how it works to understand that there are different natures, just like God has different natures wrapped up in the. I mean, He has one nature, but there are different parts to God, and that is described as the Trinity. And so I think light falls into one of those categories where we may not completely understand it, but we can still accept it as fact, just like we accept the Trinity. Okay, so our objectives for today's video were to establish the three ways that light acts as a wave and describe the dual nature of light. So don't forget your 5 questions, and there is still more that we need to learn about light. There's one more video.